So in this particular lecture we are going to talk about the instrument of the X-ray machine, or that's the X-ray diffractometer. So those who have not watched the previous lecture, I'd advise you to at least watch the last two lectures where I have talked about XRD basics. And if you're interested only for XRD, then probably you can start with lecture 3, 4, and this is the 5th lecture where we're going to talk about the X-ray diffractometer, the machine which is basically used to record XRD data. So what we have here is a simple instrument which looks simple, but the cost is quite high. The cost will actually go up to as high as 1 crore for the lowest standard model, and if you go for higher models it will definitely go above that price. So the three basic elements that an X-ray diffractometer has is an X-ray tube, a sample holder, and an X-ray detector. Now if we have the X-ray tube here, this will actually generate the X-ray, and with some other arrangements will allow the X-ray to fall on the sample. The sample is placed on this sample holder. So this is your sample holder, and the X-ray after getting diffracted is collected. The signal is collected by a detector, which is also not a very simple arrangement because we have got some other things like a solar slit and so on. Okay. So these are the three basic elements of an X-ray diffractometer. This is how a real machine looks like. This belongs to Penalitical. Okay, company is the Penalitical company. It basically uses configuration which is theta theta or theta 2 theta depending on what kind of machine we are using. Here also we have this, and this entire setup is basically called the goniometer. So you can look into this term which is basically called the goniometer. We are going to look into more details of that. But before that we have got something which is called the global mirror. The global mirror is connected on the X-ray side, okay, on the X-ray tube side. Actually these are special mirrors which are designed for reflection of X-rays. Now X-rays are generated, but I need to reflect the X-ray and direct them towards the sample, and that is where the global mirror comes into the picture. Okay. The next we have got the X-rays which are actually emitted by the sample is being analyzed by are analyzed by collimated by parallel copper blades. So this sample which emits the X-ray, okay, this sample will actually, the X-ray will fall on this sample and it will get diffracted, and this will be actually analyzed by the detector. But before going to the detector, they are allowed to pass through a slit which is called a solar slit. Please remember the spelling, it is SOLLER. This solar slit usually collimates the X-ray and makes it parallel. Okay, this entire setup including the detector, the sample holder, and the X-ray tube is known as the setup is known as the goniometer. This basically is nothing but the instrument that either measures an angle or allows an object to be rotated to a precise angular position. Now you see the setup is such that I can rotate the X-ray tube, I can also rotate the solar slit. Whether I keep the X-ray tube fixed or not depends on what kind of configuration I am using, but in general it's possible that I can rotate it. So this entire setup is called the goniometer. So the goniometer has the attachment of the X-ray tube and the X-ray detector and the sample holder, and all of them can be rotated according to our will and as per requirement. Okay. So this is important. What are the three basic elements of a X-ray diffractometer? Now if you go into the details of goniometer, I think this is something which you might have seen or you might have even used it in your classes. Sometimes it's also available in a normal standard geometry box. Okay, and this is basically a goniometer. So what happens is, this is a scale and this is also a scale, and if you want to measure the angle you can use this. Okay, you can rotate this scale along this direction and you can place it at different position to measure different angles at different lengths. Okay, so what happens is, if we actually put the detector here, okay, so if we put the detector here, and if we put the X-ray generator here, we put the sample somewhere here, and we put the X-ray detector somewhere here. Okay, so if you look into this, this is the setup. Okay, so if this is your X-ray source, okay, so this is your X-ray source, and then we can have the sample here. This is your sample holder, so we can have the sample here, and then we will have the detector somewhere here. Okay, this is the detector here. So this is the analogy with the goniometer instrument that we usually see. So it's basically nothing but a scale designed to measure the angle between the incident and the refracted beams in an X-ray diffraction analysis, a very important part of the instrument. Okay, and the instrument is basically, or the goniometer is usually used to maintain the angle, okay, and rotate the sample together. Okay, and the angle maintenance is also very important, because whenever you are plotting a graph for XRD, you have one side intensity and on the other side we have got 2 theta. Sometimes we also plot theta, but this is where we have it. So we have the intensity on this side and we have the theta on this side. So this theta is nothing but the angle which is being managed or controlled by the goniometer here. So we have the X-ray source, and the X-ray will leave the source from here. How are X-ray is generated, we have already seen in our last lecture, but we can again have a look at it now in the next slide. And then we have got the incident optics, which is basically has got this, I think I have told you in the last slide, Gobel mirror. So we will use this Gobel mirror here, and there are some more optics, some more slits and all which are present, which allows intense beam of X-ray to fall on this particular sample. Okay, and then we have the receiving end where we actually have the solar slits, and after it passes to the solar slit, which collimates the incident or the refracted beam or the diffracted beam, and it is then finally received by the detector, which is connected to electronics to get the data or capture the data and store it. Okay, so this is exactly how a simple XRD machine is operated. Okay, and then if we look into the working, we already know a part of the working. The first thing is first that the X-rays will be basically generated. So we know that the X-rays are generated in a cathode ray tube. Now how do we do it? We basically heat a filament to produce electrons. Okay, and when these accelerated electron hits a target, so in many cases the target might be copper. Okay, because if you remember in our last class we said that the copper has basically got a wavelength of 1.4554 angstrom. Okay, so we have got the wavelength of 1.45 angstrom here. Okay, and then what happens, the electrons are generated and they will hit the target, and that will be applying a voltage. Okay, and the target material is bombarded with a number of electrons. Now when these electrons will have sufficient energy, they will dislodge the inertial electron of the target material, and then definitely we will be having some characteristic X-ray spectrum, because if we have the dislodging of the K shell electrons, there will be electrons from the L shell or the M shell which will come and occupy. Okay, so if it occupies from L to K, we will be having the alpha lines. Okay, and if it occupies from M to K, we will be having the beta lines. If you are not very clear about it, please refer to lecture number 4 where I have discussed in detail. Now these spectra will consist of K, okay, I have missed out the term here, this will be alpha and this will be beta. So it will basically consist of the K alpha and K beta line, and then K will consist basically in parts of K alpha and K beta. Okay, and then what happens is K alpha will be having a slightly shorter wavelength. Okay, and twice the intensity of K beta. So we have to remember this. So the intensity of K alpha line is much high, and as a result of which we are using K alpha line, and we are not really interested in using the K beta line. What happens as a matter of fact is these K beta lines will actually interfere with the signal, and probably it will sometimes mix with the noise as well. Okay, so we might not be able to get a very clear signal. So many a times this K beta line is actually filtered out by using out some kind of filters. Okay, so the specific wavelengths of the characteristics of the target material, we use copper, iron, molybdenum, chromium and so on. Okay, but mostly we use copper, and molybdenum is also our next mostly used source, but the intensity is less, so copper is preferred. So filtering by foils or crystal monochromators, so we basically use crystal monochromators or foils to filter out some unwanted signal, like the, let's say, the K beta lines. Okay, and this is basically done to produce a monochromatic X-ray. Now if you have just the K alpha line, that means you have got an X-ray of a single wavelength. Please understand this, if you are talking about visible light, we will have 7 different wavelengths that we are talking about. Okay, and even if you consider red, there will be a number of wavelengths which are present. Something will be a lighter in color, some will be darker in color. So if you want a monochromatic source of light, that means you should have a light of a single wavelength. Similarly, X-ray is also a kind of electromagnetic wave. So there also, if you want to have just a single source of wavelength, we need to filter out other sources. So K beta lines can be filtered out, and we can actually get only a monochromatic X-ray which is needed for diffraction. Okay, so K alpha and K are so basically what happens is, if you look into K alpha, this should be, sorry, this is again missed out here. So it should be K alpha 1 and K alpha 2. Okay, this is K alpha 1 and K alpha 2. Now K alpha 1 and K alpha 2 are actually very close to each other. Okay, and they can be considered to be almost monochromatic in nature. So when we consider the wavelength of the incident X-ray, that is 1.454 angstrom, this is nothing but the average of K alpha 1 and K alpha 2 line. Okay, and as I said, copper is the most commonly used target for single crystal diffraction. Even in powder diffraction we are using that. Okay, and then this CUK alpha, sorry, radiation is nothing but 1.5418 angstrom, if we want to be precise, up to the 4th decimal place. Okay, so please remember these. There are a lot of information on this slide. Okay, and then what happens is, these X-rays are then, which are generated using these conditions, terms and conditions that we already had, are collimated, and then it is directed onto the sample. So it will finally fall onto the sample. Now what happens, the sample and the detector are rotated, and the intensity of the reflected X-rays are recorded. Now in some cases the detector is rotated, sample is rotated, but the source is kept fixed. Okay, and that we will go into the next few slides, we will see that. Okay, but right now we have to understand that we need to rotate the sample in order to find out all the possible planes, and the detector is also rotated at certain specific angles to capture the diffracted X-rays which are coming out from the sample after refraction. Okay, so when the geometry of the incident X-rays impinging the sample satisfies the Bragg's equation, so we remember our Bragg's equation. Okay, lambda is equal to 2d sin theta. Please never forget this, very important. We can find out a number of parameters from this particular equation. Okay, so d is the interplanar spacing, lambda is the incident wavelength, okay, and theta is the Bragg's angle, and so on. So when it satisfies this Bragg's equation, we will be actually having a constructive interference. So what is the condition for constructive interference in X-ray diffractometer? It is nothing but the Bragg's law. Okay? That's the simple objective question. And when it satisfies this Bragg's law, a peak intensity will occur. That means we will having a number of constructive interferences, and the final signal will be having some kind of intensity. Okay. Then the detector, what happens, then that happens in the sample. It should satisfy Bragg's law so that we can get the signal, and then this signal is recorded by the detector and processes this X-ray signal. Okay, and this will actually convert it into a readable signal, okay, into a count rate, okay, which is then taken out in a device as a printer or a computer monitor to look into it. Okay, so whatever images or the XRD data you get is basically going to these processes for the final output. Okay, so if we consider the X-ray diffractometer, okay, it can be rotated, and we have to rotate it along only a certain angle, and the data is mostly collected for at 2 theta from 5 degree to 70 degree. There are some issues if you go above 70 and below 5 degree. I'll tell you probably in the next slide. Let's look into one of the images here. So you look here, this is the image that we have. Okay, so what happens is, this is basically called the Plantino Geometry. Okay, so this geometry is very important to understand in order to know what is this theta and 2 theta configuration. So basically in this particular diagram we can see this is a theta 2 theta configuration, and this is the configuration based on which an X-ray diffractometer works, and that comes from the Plantino Geometry. Okay, so it is the geometry of an X-ray diffractometer. It's such a way that the sample will rotate in the path of the collimated X-ray beam. So we have the sample which will rotate in the path of the collimated X-ray beam at an angle theta. Okay, so this is your angle theta here. So the sample will keep on rotating. So we can consider this angle, and this will basically be theta, and the sample will keep on rotating at that angle theta. And the X-ray detector is mounted on an arm to collect the diffracted rays and rotate at an angle 2 theta. So if this is the direction of the incident X-ray beam, and this is the direction of the detector, the arrangement is made in such a way that this angle will nothing be but be 2 theta. So that means the sample is rotating at an angle of theta with respect to the X-ray tube, and the detector is rotating at an angle of 2 theta with respect to the X-ray that is coming from the X-ray tube. Okay, that's as simple as that. Now you understand this, that as I told you that this varies from 5 degree to 70 degree. Okay, that is important. Now if this angle keeps on reducing, what happens is this will keep on reducing, okay, and then this angle will be very small for the X-rays to actually hit the sample and get diffracted, okay, and as a result, if we go below 5 degree, we are not going to get much of a result. There is another concept of grazing angle which will be coming into the next lecture. On the other hand, if we actually look into this 90 degree, okay, 90 degree or 70 degree, we can go up to this point. Now if this basically goes in a larger angle, okay, in a larger angle, we can actually have a different scenario. We won't be receiving any kind of signal there, okay. But before we do that, let's try to understand few of the basic concepts. So the same thing, which is nothing but theta, is also the incident angle, and this is the angle between the X-ray source and the sample. So this is what is omega is all about here, and the diffraction angle is usually called as 2 theta because that is the angle by which the X-ray is diffracted, and this is the angle between the incident beam and the detector, as I told you in the last slide. And this incident angle is half the detector angle 2 theta. That's quite obvious, okay. So if you consider an instrument where there is a theta 2 theta configuration, okay, there are two kinds of configuration. One is theta 2 theta configuration and one is a theta theta configuration, okay. So in a theta 2 theta configuration, the tube is fixed. So you have this part as fixed, okay. So in a theta 2 theta configuration, this tube is fixed and the sample rotates at 0 degree theta degree per minute. So this sample will keep on rotating at theta degree per minute. So if you fix it at 1 degree per minute, that is you are having a very good scan rate, okay, so that you can analyze each and every part of the sample. So if this theta degree per minute is low, let's say 1 degree or 0.5 degree per minute, you are going to get better results because the X-ray that are incident on it is going to interact with all the planes very clearly, okay. If you rotate it too fast, you might not be getting a better or sharp peaks, okay. So and the detector rotates at an angle 2 theta degree per minute. So this detector will also rotate, but this will rotate at an angle of 2 theta degree per minute, okay. So that's basically for theta 2 theta configuration. Now if you look into configuration theta theta instrument, there what happens is we basically have this sample is fixed. Now here this sample is fixed now, okay, this is fixed, this does not move. Now the tube rotates at an angle theta degree per minute. So this tube will rotate in this direction at a speed of theta degree per minute, and the detector rotates at an angle theta degree. So this detector will also rotate at same speed, okay. So this is also theta and this will also be theta, okay. So you can see if it comes here and basically goes here, the angle that it makes with the sample will become 90 degree, and there is a possibility that this X-ray tube will hit the detector, okay. This is something which we don't want. That's the reason that that is also a reason in theta theta configuration or theta theta instrument that we always keep the angle below 90 degree. In fact, I've said 70 degree, that's the usual practice, but even if you go up to 80 degree, you will be able to get some signals, okay. So if this is at 80 degree, the detector X-ray tube, or let me take a different pen here, let me take a black pen probably. If this is X-ray tube is 80 degree, the detector is also at 80 degree, there are chances are there you will be getting some kind of signal, but at 90 degree you are definitely not going to get any kind of signal, okay. So this is what is the Plantino geometry is all about, very important. And we have got something which is called the diffraction vector. Diffraction vector is this S, okay, and this diffraction vector is always normal, or it will basically bisect the angle between the X-ray received from the X-ray tube and the diffracted beam, okay. So always it is always normal to the surface of the sample, that is also important. It is a vector that bisects the angle between the incident and the scattered beam, okay. So that is the diffraction vector. So what is the position of the diffraction vector, or how is the diffraction vector determined, might be a question, one mark question, and probably this should be your answer, okay. So we have a number of materials that we can analyze using X-ray. We have got a single and polycrystalline material. I think we have already discussed about single and polycrystalline materials before, but in general, if you consider a single crystal specimen, that means we have got only one set of planes possible, okay. So if you consider a single crystal specimen in a Bragg-Plantino diffractometer, it will produce only one family of peaks in the diffraction pattern. Now I hope all of you remember how to actually find out the Miller indices which will represent the plane. For that, first you need to know what is the intercept. Okay, so if you basically draw any kind of structure here, okay, and let's say we have got point 3 points here. Let's say we have it here, we have it here, sorry, and we have it here. Okay, and then what we can do is we can actually make some lines to join them, okay, and then join them, okay, and let's say this is half of each of them, okay, and then this is the plane that we are talking about. Okay, so once we know the intercept, we can actually know what is the plane. So what is the intercept here? So let's say this is your x-axis, okay, this is your x-axis, this is your y-axis, this is your z-axis, and let's say they are intersecting at half. So maybe we can consider this as half, this intercept is also half, and this intercept is also half. And now if we want to find out the Miller indices, how do we do that? We simply just take the intercept, the reciprocal of the intercept, and then the Miller indices will be nothing but 2, 2, 2. So 2, 2, 2 will represent all such planes. Okay, so 2, 2, 2 will represent all such planes. Okay, we have it here. So we have one plane here. If you want to have one more plane on top of this, okay, so we can have one more plane on top of this on some other, because this is a unit cell, this will be another cell, but this will be on top of this, okay, and then this will keep on going. So what we have is, if we consider this 1, 0, 0 plane here, if we consider this 1, 0, 0 plane here, the next 1, 0, 0 plane will be actually behind this. Okay, so this is going to represent a family of planes. So the beauty of Miller indices is it is going to represent the family of planes for the entire crystal system. Okay, but on the other hand, if we consider something like 2, 0, 0, 2, 0, 0, that means the intercept is somewhere at the middle. Okay, it is not at the edge but somewhere at the middle. 0, 0 means they are intersecting at infinity. Okay, so they does not have any intercept with the x-axis or the y-axis, and 2 means it is going to intercept at half. Okay, half of the x-axis. So this is something which you should know, and that means that if we consider that 1, 0, 0 will belong to a set, 2, 0, 0 will also belong to the same set. Okay, so that means that if we are actually having a single crystal material, and let me just draw a graph, I don't have space. Okay, let me just take a different color marker here. Okay, so if we take this and we actually plot an XRT graph, and then you can expect Miller indices here, and you can expect Miller indices here. Okay, this might be some value of theta here. Okay, and then the plane that we are talking about are nothing but let's say this would be 1, 0, 0, and this would be 2, 0, 0. So if you take a single crystal, you are going to get a 1, 0, 0 plane and a 2, 0, 0 plane. You are going to get both of them. Okay, the intensity might be lesser for 2, 0, 0 and so on, but that means it's basically a single crystal. You might not be observing any other peaks. Okay, so if you're considering a normal polycrystalline material, let's say for example tin oxide, you may be having more peaks there. This peak might not be observed when you are considering just a single crystal specimen. But on the other hand, if you are considering something like a polycrystalline sample, it should contain a number of crystallites. Okay, and then you will be having planes which are directed in all possible directions. So that means all the planes are possible for that polycrystalline material. Okay, so you will be having a number of diffraction peaks there which will be observed. Okay, so it will be totally different from a single crystal material. But you have to note that most of the work that you would be doing in future, or if you are working on nanomaterials and all, it will be polycrystalline in nature, but if you are working especially on single crystal materials, then also you can do that. Okay, but people usually in India, we work mainly on polycrystalline material. Now for every, you have to note this, for every set of planes there will be a small percentage of crystallites that are properly oriented to diffract. So that means if you have got a certain designated number of planes, then only you are expecting to get a peak. If you have less number of planes in that particular direction, the peak will be there, it might not be visible, it might be mixed with noise, or it might be very less intense. Okay, very less, the intensity might be very less, and so on. Okay, so if the intensity is high, you can understand that there are a number of planes which are aligned in that particular direction. Okay, so I hope you understood the essence of this particular slide. Please try to refer to previous lecture also for understanding the XRD basics. Okay, so this is what we have for today. For the next class, we are also going to see into some more technical terms of an XRD instrument. Thank you.